My name is Professor Joseph Wunderlich. I teach computer engineering and also architecture, building architecture as well as computer architecture. This lecture is a very quick flyover of this paper, book chapter, a mix of research I've done in the past, a paper and won an award on that is covered in detail in machine intelligence class through lectures that we won't do here. So the idea is a top-down versus bottom-up neurocomputer. And by that, you see in these two diagrams here, what you see is a biological neuron versus a mathematical or psychological kind of control system model. And that's what the meaning of bottom-up would be from the biology perspective. Top-down would be from the mathematical or control theory perspective. Then the analog or the model of the output transient voltage of a biological neuron is, can be modeled like this, this RC network of resistors and capacitors. I built a chip like this. And then the top down, you'll see different models that are compared here. You have to go back in the history and look at backpropagation, Madeline, Hopfield, Boltzmann machine, and BAM and neocognitron. So those were picked, and then you'll see some of the rationale for the how to do the digital or analog of that circuitry based on the learning or the neuron transfer function. You see a comparison here. The bottom up is an analog circuit of resistors and capacitors and some switching. And then below is this mathematical model, or this typical neural network model that you see for backpropagation. Then continuing for the backpropagation, there's talking about the functions, the transfer functions, and the weight changing functions, and how those are put into algorithms. Then there's some sample code here for doing that, and more sample code, more simple sample code, a little more. Then you start seeing these numerical methods I use to approximate curve fitting the continuously differential transfer function using polynomials with the hope of going fully parallel with polynomials and all digital on a chip. And you see the error below here, analyzing the error in the bottom graph. And various different mathematical numerical methods and the error associated with each of them. And there's plus and minus associated with each, so you have to look through that. Just different models and different error. And then I got it nailed down to one that I picked. And then there's always, with these numerical methods and these polynomials approximations, they're only good for a certain range. So I asked myself the question, could I clip it off at certain points, like just it's getting up near the asymptotes at 1 and 0, these sigmoids, and so can I just clip it off where it starts losing the polynomial approximation, just is not accurate anymore. So then I coined this thing called the clip sigmoid. I played with that and showed that that can still learn. Then you see some code with the clipped sigmoid. And you're clipping at different points, and also the different numerical methods. So you see in the summary in the beginning, the clipping at different parts of the range, and also the numerical method used for approximating a polynomial. And there's code for that, more code for that, still more code, but different polynomial approximation methods. Still more code. And then we look at gradient descent learning, analysis of what's, what am I tweaking here? I'm, want to look at the learning. So look at the mathematics and the calculus. So there's a derivation of that. And you can see them minimizing the sum squared error here is the idea of the differences between the desired outputs and the actual outputs. That's the error that I want to minimize, and I want to change the weights with respect to that. So you see the partial derivatives and the calculus involved in that. And then you see the breakdown of the calculus using the quotient rule and different parts of the calculus involved. And then the graphs below here, you're looking at the fact that you're using the derivative, you're changing weights based on the derivative, the slope of the curve of the transfer function, which is maximum right at x equals 0. So you see on the right-hand graph there, the rate of change is maximum right at the middle. That tells you that the neuron is deciding which way to go, and you're magnifying that, this gradient descent, and that helps with the learning, is magnifying the decision process in the middle range there. So this above calculations here is the backpropagation of the error from the output neuron to the hidden layer. Now we have to extend that with the multivariable chain rule, taking that backpropagating the error signal through those weights into the hidden layer, and then between the hidden layer and the input layer. We're changing the weights between the hidden layer and the input layer now, and so you see the same kind of thing going on. The calculation is a little more complicated because you're carrying through the whole weight change from the end to the beginning of the network. Then you see here a chip that I built for the bottom-up approach, and then the top-down was looking at it was a mathematical analysis and a paper design and of a neural network chip, and also the analysis for doing the clip sigmoid. And so that was part of the patent disclosure document I did in 1992 for the top-down method. Compared to what you see with the chip design there for the bottom-up method. And just a couple more references. So you certainly want to go back and look at this in depth, and there would be other lectures more. This is more of an overview lecture.